You can also make me a co-host. So you have a meeting, Arka, at 8 o'clock, yeah?
Yeah.
Okay. But we can wait for a few minutes.
Yeah, I mean, it's not like, it's okay. I mean, I don't think that, I mean, what I will present will be more than 1 hour. Definitely not
Okay.
more than 1 hour.
Right. So today's timing is unusual. So maybe some usual attendees will join at 7.
Okay.
Do you have slides?
Yeah.
Yeah. Please share them.
Okay. Are they visible?
Yes.
And is it like too small or like big enough?
It's okay because it's just the title page. I don't know what happens next.
Okay. I guess like
It's
this.
possible, right?
Yeah, you can hide the sidebar.
Yeah, the full screen will be
Full
fine.
screen option is better.
Okay, let me.
Thumbnails you can remove. I think that is the.
Yeah.
Yeah.
But it's the same size, I guess. Maybe I can. Oh no, too big. This is okay, right? Or is it?
Continuous scroll is also okay, I feel.
I guess, yes. Oh no.
Yeah, this is better. Like the size is font is big enough.
But this will become like not the full PDF.
Okay.
Maybe I can do single page, but
Generally, it's Command L. If you just press Command L, that should work.
oh no.
No?
Yeah, it's usually this also works.
Yeah, this is okay.
So did the size change or is it the same?
Slightly bigger.
Okay.
Shall we start?
Yeah, sure.
Yeah. So welcome everyone to this mini series of talks by young researchers in logic. So today we have Mr. Arka Ghosh from University of Warsaw, Poland. He will speak about sets with atoms or computation with infinite sets. Both titles have been given, so let's see.
Okay. Can I start?
Yes.
Okay. So first of all, thank you the organizers for organizing this series, and it's I mean, I really like the talks. I mean, most of them that I attended. So today I will talk about sets with atoms, but before saying what is sets with atoms, I will give some examples of things. I mean, why we discuss this. And so the purpose of discussing sets with atoms is to like build a framework for models of computation which work on infinite data. So what's an example of that? Consider this like consider the model of register automata, which means this automata, but each state has some value in it. Okay, so the letter inside it is called like the value in the register. So this automata, as you can see, it's like a 3-state automata. And in the first state, in the start state, it has this bot symbol, which is like nothing. And if it sees any letter, it goes to the next state and stores that particular letter in the state. And if it sees some letter, it checks whether the letter is same as the letter stored in the register, or if it's different. If it's different, then it stores the other letter, the next letter in the register, because like if B not equals to A, then A goes to B. And if it's the same, then it goes to the third state, which is like kind of the sync state, and it just stays there. So this state, the middle one, is the accepting state. And I guess, I mean, anyone wants to guess what kind of like what's the language for this automata? Any guesses?
A star, right?
No, it's not star. I mean, if you see like
You
it's
keep on, okay, A, B star or something like that.
no. So A is not a particular symbol. A is just like a variable kind of things. Like it's any letter. So the automata starts with like in the starting state with bot.
Yeah.
And if it sees any letter A, it goes to the next state, this violet state, and stores that letter in the state. Because I mean now because I'm discussing the register automata, it's like each state has also like a small memory. And so
I have a question here. Like you are using the letter A also as a label of arrows and A as label of the state. So,
yes. So A is not a level of the state. A is what is inside the register of the state. So each state is, so the states are colors, not the letters inside it.
okay.
So each state has also like a memory inside it where it can store some data. And the data it stores, at least for this example, is the letter itself. So at each point it checks that the letter it has, is it the same as the letter it has on the memory? If it's the same, it goes to the sync state. If it's different, it stores the next letter in the memory and keeps doing the same. So this violet state is itself the accepting state. So I mean, so yeah, any guesses of what kind of languages this automata accepts?
So all strings which have a letter which is repeating consecutively. For example, like,
No. So this, because this is the sync state is not accepting, the middle state is accepting. So this will accept any string which doesn't have any consecutive letters the same letter, right? Because
yes,
then, right? Is it okay?
yes. Thanks.
Because if it's different, then it will keep doing the same. It will keep being in the center state, like in the violet state, and keep storing it again and again. And also because the starting state is not the accepting state, it has to accept only, like it will accept only strings which are non-empty. So all non-empty strings which are okay, I can't. Yeah, all non-empty strings which doesn't have any same consecutive letters. And if you see this particular model, this can work when sigma is infinite, right? Assuming that I can store the letter in the state, this model works even when sigma is infinite, right? There is no restriction which keeps us, like which makes us to say that sigma has to be finite. So sigma can be infinite. So this particular model works on sigma, which is infinite. So this is like a model of computation which works on infinite data. Right. Yeah. And yeah, now, I mean, the application, this is some application in maybe like some kind of semantics, but let's not discuss those here. So let's say another model, which is like a timed automata. So what's the timed automata? For now, I will assume the time automata is like, okay, let's see the example. So this is to model like a person who is living at home, and he's a cook, so he has to go to the kitchen and in the toilet because the cook has diarrhea. So he has to keep going on to and from the kitchen, and from the kitchen he has to go to the toilet and back. But so the C is a constant. And what this kinds of things is like, what it says is like, if the person stays more than 10 minutes in the toilet, the food gets burnt. So the state, how it goes like this. So a timed automata actually takes a language from the alphabet, some finite alphabet with a timestamp. But for this one, I have assumed sigma is equal to like singleton set. So for this one, the alphabet doesn't matter, only the timestamp matters. So this will accept all possible timestamps, like time intervals. So at 0, it will be here. At T1, the person will go to kitchen. At T2, it can go to back to home or to the toilet, and T3 it can go like this, like that. So I mean, the only condition is, so at each point, it will see how much time it spends at a particular state, right? Or how much time it has spent at somewhere like before coming to the state. And all these edges has also a guard. So phi means there is no guard. Anything can pass through. But C less than equal to 10 means when it passes through, the guard C has to be less than 10. So, okay, maybe you can think it like this. When the automata runs, it has a clock with it. So for going from home to kitchen, the clock, there is no constraint on the clock. From going to kitchen to toilet, it sets the clock to 0. And in the toilet, it's taking, if it's less than 10. So in the toilet, if it has to see that the clock doesn't cross 10. So it has to come back from the toilet before C is 10. So that's a automata model with a clock. That's why we called like a timed automata. And yeah, so this model will accept all such timestamps or time intervals such that the person doesn't spend more than 10 minutes in the toilet. Okay. So this is also a model which works on infinite data because the timestamps are from rational numbers. So this can be infinite. But if you see both of these models, like timed automata and registered automata, their representation is sort of finite. It works on infinite data, yes, but how we like write them is finite. So all the constraint, all the states are finite. So this is like so we need to build a framework for these kind of computation models, which can be represented in a finite manner, but they work on infinite data. Okay. So for this, we have this particular thing called sets with atoms. And I mean, it's not a very new thing. It started, I think, it started by Frankel and Mostovsky. And they started like discussing this for building a set theory, which doesn't satisfy choice axiom. And then Gabay and Pitts recently sort of rediscovered it in terms of nominal sets, but they used it for different things for building a semantics to work with names or variable names. And then also, I think Pistor and Montanari also discussed these name sets where they were discussing Petri nets with data. So yeah, but yeah, what are those? So sets with atoms are sort of like a set structure with something called atoms. So we need to first see what are atoms. So atoms, we can say like a set with certain structure. Usually we assume A to be countable infinite because I guess what we are discussing now is mostly in the model of computations. And I think for model computations, thinking of uncountable data doesn't make much sense. So a countable data makes more sense, but yeah, for now, we don't need to think about that. And so aught A is the set of all structure preserving isomorphisms of A. And elements of A will be called atoms. But what are some examples? So we can take rational numbers with order. So the set is the rational number, like the set of rational numbers, and the structure is the order. And aught Q will be the set of all order preserving bijections, right? So this is like a set structure, and aught Q is the all structure preserving bijections. So we can also assume natural numbers with equality. I mean, equality means the only structure that is preserved, that ought n preserves, is equality, which is preserved anyway. So ought n is basically the set of all bijections. So we call this, the first one ordered atoms and the second one equality atoms. And these two atoms are the most discussed atoms, at least in the literature and also in the current research as well. So yeah. And so another thing we can think it as is a pair X comma G, where G is a group and X is a G set. I mean, as you can see, like the group itself, the automorphism group itself kind of fixes the structure. So you can also think it like that. But there are certain reasons where we don't use the second definitions and use the first definition, which, I mean, there's also like the reason can be because the first one is more easier to see. The second one is more abstract, but the first one is more concrete. You can like see what's happening. And also there is, it's easier to build. I mean, it's easier to build atoms thinking from the first definition.
So, sorry, so elements of such a set. So which set are you talking about?
Sorry,
A
yeah,
or
it's the
odd A?
yeah, A.
Okay.
So A is like set of atoms and odd A permutes those atoms. So yeah, and this is the definition. And now we have to build like a whole set theory based on atoms. So before building the set, we define something called preset A. And so preset A is a like, how do I say, like indexed set indexed by alpha and alpha ordinals. So it's like stacked kind of thing, like a one Newman universe. So phi belongs to preset 0. So it's 0. So phi is in the 0 level of preset 0. Sorry, preset A. And if there is a set X in the alphath level of preset A, and I mean, so a set can only be in the alphath level of the preset A if for all Y inside the set, either, I mean, if all elements of X is either in lower levels or their atoms. So it's like a one Newman universe, but you start from, I mean, other than elements of the previous level, the sets can also contain atoms, elements from atoms. And yeah, so maybe I can see what some examples. Okay. So one example can be, let's say you are taking equality atoms and like n equality, like natural numbers with equality, and you can assume the set phi, like phi comma 1 inside a set, that's set with atom. So also, I mean, yeah, so you can build it like this. So it's a one Newman universe where each element can contain elements from lower level and also atoms. But this element is not very useful because all elements of preset A are don't really have like a finite representation. Even we allow to use atoms as constants. So yeah, we will see what that means. So because it's an automorphism of A has like a group action on each element of preset A by simply pi capital X is the set of pi small x for all x belongs to X. And you can define it because this goes to all levels, right? So the group action in one level helps to build the group action in the next level. For example, if you think this set like, so swap A comma B is a permutation which swaps A and B, and all A, B, C are atoms, and phi is just phi, then empty set. So swap A comma B and this set A and the set B and set C and set of empty set, it just swaps the atoms A and B and keeps everything fixed. So this is, yeah.
What is the meaning of hereditary?
Hereditary means like the group action doesn't only work on the set, it also works on like each level. So it's like set, elements of each set, elements of each set, like that.
So it works on preset A alpha for
Yeah, so for all, I mean, preset A is the union of all preset A alpha.
right.
So the hereditary means like because aught A is already like a group action on atoms,
Mhm.
and you are building preset A as a von Neumann structure where each level, like element of each level has elements from lower levels or elements from atoms. You can define like you can extend the group action to preset A itself, right?
Right.
So this is the group action. So okay, so I mean, is everything clear up to now?
Yeah.
Okay, so then we have some definitions, unfortunately. So one, like x belongs to preset A supports y belongs to preset A. If and only for all automorphisms, pi x equals to x implies pi y equals to y. So if automorphism fixes x, it has to fix y. That's why we say x supports y. And we say x belongs to preset A is finitely supported if there is a finite tuple A of atoms such that this atom supports x. So there is a finite tuple. If you fix the tuple, the whole set x would be fixed. For example, yeah. So take three atoms A, B, C in A, and take this atom like set of set A union all atoms minus the atoms B and C. So this particular set is supported by A, B, C, right? Because if any automorphism fixes A, B, C, it may permute something inside A other than B, C, but the whole A slash B, C will be the same, and thus A will be the same. So the whole set will be the same. Okay. Yeah. So one thing you can think is like finitely supported means you can sort of describe the whole set using only finitely many atoms. So that is the kind of intuition behind defining the like having the definition called finitely supported sets. Because yeah, so if you let's take like a countable subset of atoms A0, A1, A22, yeah, and then this particular set like A0, set of A1, set of A2, then set of A3. If you continue like in this manner, this particular set won't be finitely supported because any swap, any change will change this particular set, right? So to fix this set, you need to specify all those atoms. So that particular set, the second one, cannot be defined, cannot be described using only finitely many atoms. That's the idea. So it's like that's why this set is not finitely supported. Fine. Okay. And so yeah, so set A, which is called the sets with atoms A, is that particular subset of preset A, which contains all hereditary finitely supported elements of X. So what does hereditary here means? Which means X has to be finitely supported, elements of X has to be finitely supported, elements of X has to be finitely supported. So it's like you can describe X using finitely many atoms. Not only that, you can also describe all elements of X using finitely many atoms, and like so on. So that's the yeah. And okay, yeah. So there's a set A comma phi and A minus B. So this A comma phi is the whole set is finitely supported by A and B. A comma phi is also finitely supported, and everything else is even inside it also finitely supported. And also this particular set A, set of A, and like so on. This particular set is also supported by small a, right? Yeah, I mean, so this particular set, if any automorphism fixes A, the whole set will be the same if you apply the automorphism on it. Okay. So, okay, so is everything clear up to now, like this definition?
What's the curly parenthesis there? A minus singleton B.
It's like all atoms except the atom B.
So it is this set.
Yeah.
And then you are taking comma because it's a pair.
Yeah. No. So it's like a set of 1 a comma 5, and the next set is the set of all atoms except B. So it's a pair. I mean, it's not an ordered pair, it's an unordered pair.
It's unordered pair, but
Yeah.
so you don't want to say curly parenthesis there. Yeah, like singleton curly parenthesis, that's not your goal. I mean,
So this is like A minus B, like the whole set A except the element B.
okay. Fine.
Yeah, it's not the like it's, yeah, I don't know. Maybe it's a bit confusing.
That's okay.
Okay. So yeah, next we have a bit more definition. So orbit of a particular element X, this orbit A bar X is the orbit of X using only automorphisms which fixes A bar. So you are saying like if you have X and you can create the whole orbit by applying all automorphisms which fix A bar. And we say like a particular set is orbit finite if it can be written as finitely many orbits. So I mean, this is like same as group theory, but we just have one more definition, like one more notation A bar to say that what kind of automorphisms we can apply to get the orbit. So this is the definition of orbit finite. And as you can see, like each orbit is actually supported by like this A bar. So orbits are automatically finitely supported by definition. And yeah, our favorite sets are hereditary orbit finite sets, which means, I mean, although we sometimes we will like use elements from set A, but most of the times we'll try to use elements which are orbit finite with orbit finite elements and like so on. So yeah, and now so now I have some examples. So this particular set A0, A1, set of A1, set of A2, and so on. This is neither finitely supported nor orbit finite, and also of course not hereditary orbit finite. The next one is A, set of A, and so on. This is finitely supported because it's supported by the small a, but it's not orbit finite because each element of this particular set is itself an orbit. Because if you apply like any automorphism which supports A, that has to like, so that can only like create like a singleton. So this set is finitely supported, but not orbit finite and neither hereditary orbit finite. And the next set, which is like B, the same set, but now we are taking all such sets for all such atoms. This set is finitely supported. This is orbit finite because if you apply any permutation, the B will change to C or D, but that's already inside that particular set, so it's orbit finite. But because elements of this set are not orbit finite, this is not hereditary orbit finite. And in the end, we have the previous set, which is finitely supported, orbit finite, and also hereditary orbit finite. So as you can see, there are two possible sources of infinity here. One source is how many atoms you need to describe the particular set. Another source is sort of like the classical source of infinity. So the second one, like A, set of A, set of A, this source is like sort of, it's classical infinity. So in these two particular senses of infinity, we very much dislike the first one, like that, like when you need infinitely many atoms to describe the set. But the classical infinity, we don't like it, but it's still okay. I mean, we can still agree with it. But our favorite sets will be when it's like finite, it's like both finitely supported and orbit finite, and also like hereditary orbit finite. So it's like orbit finite at each level. And there are reasons to why we like them, but maybe today I won't have time to discuss all those. But yeah, so yeah, now we have this hierarchy. arbitrary sets preset A, finitely supported sets set A, and then in one set we have classical sets, and another set we have orbit finite sets. And classical sets, then we have classical finite sets, and from orbit finite sets we have hereditary orbit finite sets, and then finite sets. So these classical finite sets are atomless sets, and this finite set means it's with atoms but still finite in every level. So this is the hierarchy, and this the middle one, this set A is our universe, and but our favorite elements in the universe are this particular hereditary or finite sets. Okay, so yeah, now maybe some closure properties, because why we like these particular sets. So if X and Y are like orbit finite sets, then X union Y is orbit finite, finitely supported. So is X intersection Y, because you have like finitely many things to describe, and each of the finitely many things you can describe, like they are finitely supported. So yeah, the union and intersection also has to be finitely supported. And even if there are finitely many orbits in X union Y, in X and Y, there will be the same in X intersection Y. Well, the second one may not be true in all cases, but there are some nice class of atoms where this will happen. And then we have X times Y, which is also nice. I mean, if X and Y are nice, then X times Y is also nice. Any finitely supported Z subset of X is also, of course, finitely supported. And yeah, for some subclass of atoms, they're also orbit finite. And but any arbitrary subset may not be finitely supported, and may not be orbit finite as well, because you can take like the set of atoms, and that particular set itself is orbit finite, which is like a single orbit. Maybe you can go to one atom to another atom using any permutation, but like an arbitrary set of atoms and arbitrary subset of atoms may not be finitely supported, and also may not be orbit finite. Yeah, so then we have set of all finitely supported subset of X. This is finitely supported, because if you fix X, then all subset of X will also be fixed. But it's not orbit finite, because like if you take each cardinality of set, that will be in a separate orbit. Because let's say, like again, X is the set of atoms. Then if you take all finitely supported subset of atoms, that particular set, like if you apply any permutation, it will be come back to the same thing. But if you, let's say there is there is a set with 2 atoms and there is a set with 3 atoms, then they need to be in different orbits. So the set of all finitely supported subset of X in most of the cases is not orbit finite. And this is one of the reasons, although we like things to be orbit finite, we have to consider things which are not orbit finite as well, because the power set is not orbit finite even in this paradigm. Set of all subsets is, of course, neither finitely supported and nor orbit finite. Yeah. And set of well, actually, no, this slightly wrong. Set of all subsets will be actually finitely supported, because if you fix X, subsets will also be fixed. But yeah, but it's not orbit finite, because this set will contain the finitely supported power set. So this can't be orbit finite. Set of all finitely supported functions X to Y, this is also finitely supported, but it's not orbit finite, because like set of all supported like functions X to Y, they're like, even if you say like if you take atoms for both X and Y, that itself is the set of all automorphisms which are no way orbit finite. And set of all functions, okay, I think this also will be yes. I mean, it has to be finitely supported, but not orbit finite. And Yeah, and unfortunately, in this particular paradigm, the axiom of choice does not hold, because if you take any like a family which takes like an unordered pair and maps it to the ordered pairs like a comma b, like set a comma b goes to a pair a comma b and pair b comma a. So this, if you say we need a choice function, the choice function cannot be finitely supported, because if you fix any finite set of atoms, then you take any two atoms outside the support, you swap them or you change them, and this thing will be changed. Let's say like you take, maybe you fix some natural numbers as atoms with equality, and if you say like atoms up to some capital N are fixed, you take anything bigger than those two, swap them, and the choice function which used to maybe go to m comma n to ordered pair m comma n will now go to m comma n to ordered pair n comma m. So the choice, we can't have like a choice function in this paradigm, and this has some unfortunate consequences and some, so that's why working with is a bit different than working with classical sets. Yeah, so some things, for some theorems, like one part of them will hold and another part of them won't hold. For example, I think if you take Schroeder-Bernstein theorem, one part will hold, like from injection to bijection will hold, but from surjection to bijection won't hold, because for that you need like a choice function to go back. So these things are a bit of notions, but yeah. And okay, so I said that we use all these sets to define models of computation with infinite data. So now I will try to say how we can model those using this example again. So, I mean, let's recall the example. We have a automata, and each state of the automata can store a particular, has a small memory. Here it stores like a letter in each memory. And yeah, this is the automata. And the language is like it accepts all non-empty strings with no repeating consecutive letters. But now I want to represent this as like in terms of orbit finite sets. So what I will do here, I will assume equality atoms. And now I will define like a automata where each of the sets, like the alphabet, the states, the function, the starting state and the final state, all of them will be orbit finite. So the alphabet is atoms itself, and Q is, the states are like colored, three colored. So in sets with atoms, you also have the classical sets. So you can create something like three colored sets. And then you take cross product with atoms with this bot. So it means like three sets, cross product, contents, possible contents in the register. And the starting state is basically this blue set with bot in it. So yeah, blue cross bot. And the final states are of course this violet state. So it's like violet cross atoms. And let's see now the transition function. So it's, if it's from the blue state, it sees any atom, it goes to the violet state and stores that particular atom in the state. If it sees, if it's in the bot of the violet, it goes to the red state, which is the sync state, and keeps going there. If it sees this, like if it sees that the letter that appeared is same as the letter in the memory, then it will go to the red state and store bot, like basically nothing in the state, and keep being there. If it sees like what's in the memory is different than what's in the input, it will show the letter in the input and be in the same state. So, but as you can see, all the description is actually in terms of orbit finite sets, right? So this is, so that's why we can use this particular paradigm to represent this particular automata. And this also works for timed automata, but for that we will use ordered atoms, because now the sets, the inputs are like ordered, And that's why we can represent everything inside this paradigm. And I mean, now the point is why we want this paradigm. There has to be some gain of doing this, right? So, and indeed there is some gain. So if you see automata, this particular model, there are some automata with the registers which doesn't minimize. And but in this model, if you see orbit finite automata, where everything is orbit finite, in this automata, people have proven Myhill-Nerode theorem, like some extension of Myhill-Nerode theorem to this case, and the minimization sort of comes from this itself, because I guess Myhill-Nerode will give you, I think it's okay. I don't remember what it's called, but Myhill-Nerode will give you the algorithm for getting the minimal automata. I mean, that's sort of because you have finitely many states, so you can create the automata using only checking some up to some particular letter. So that's, I guess, the main idea of Myhill-Nerode, and you can use that one to get minimization of automata. And well, yeah, so there are three directions of research which people do. One is automata theoretic, which is people are discussing these kinds of models using this particular theory. And there is algebraic, which means you have classical theorems, classical algebra and everything. You want to do everything in here. For example, you want to solve equations where both the variables and the equations are indexed by sets with atoms. So they're like infinite. So, I mean, if you see that atoms, they're like some G set. So using this thing, you can solve equations where the variables and the equations are indexed by G sets. And yeah, so this is actually what I am doing, how to solve equations in this particular paradigm. And there's also another thing related to model theory, because now we have seen some atoms, but one question is, I mean, how to create more atoms, right? I mean, how to see what kind of structures that atom have, like, and how we can build these structures. For that, there is something called homogeneous atoms and Fraser limits. I'm not sure if I'm pronouncing it right, but they use it like so homogeneous atoms, like they say like you build the whole set of atoms from finite subsets, and these finite subsets embed very nicely inside the biggest subset. Yeah, I mean, I need some more things to describe it, but it has some nice model theoretic questions as well. So, okay, I guess this is kind of the end of the talk, and yeah. Any
Thanks a lot, Arko. I mean, it was a very gentle introduction, gentle and very well planned introduction to a completely new area, at least for me, and I'm sure for many others in the audience. Any questions for him? Okay, I have one. Like, what will you do with the second example of automaton, the timestamps and?
Oh, okay. You mean like how can I represent that?
Yes, yes. Was that like the second example n less than as the set of atoms?
It will be no, not n less than, but rationals less than, because timed automata you use rational numbers, not not naturals. I mean, and there is a reason why you use the rational numbers, because it's less than, if you see like less than 9 or 10, there's nothing like, there's nothing between 9 or 10.
Mm-hmm.
But if you use rationals, there is this nice thing called density property,
Right.
which is kind of useful when you think about time, because I mean, you want to think time as maybe not like the whole real line, because that sort of gives you uncomputable things, but at least like dense thing, like there's any between any two time interval there is a point time. Yeah.
Right.
Yeah, so this also you can represent using rational atoms, ordered atoms.
Rational atoms. Right. Any other questions? Yes, Sujata.
Yeah. So thanks, Arka, for this as I completely agree with Amit, what just Amit said, that it's a very new thing for me as well. And thanks for the very nice introduction. What I was wondering is, you mentioned at some point that our favorite sets are these hereditarily orbit finite sets.
Yeah.
So, but when you gave the examples, I think I saw only this orbit finite automata and things like that. And then you said that you need to consider those other sets also. So,
Yeah.
So can you say a bit more about this?
So because we can consider hereditary orbit finite sets, but when you go to the power set, that's not even orbit finite, right? So that's why we kind of need this everything.
Okay. No, so my question is more about trying to understand that why did you say that the
Yes. Okay. So
finite.
there are many reasons. So I mean, we define orbit finite as an extension of finite. So it should be possible to do things which are possible to do in finite sets in this orbit finite sets, the hereditary orbit finite sets. So actually there is a theorem saying for certain subclass of atoms, you can decide membership, equality, and subset with this particular sets. This hereditary orbit finite sets, you can decide membership, equality, and subset. So that's a very interesting thing. And yeah, that's because that's sort of one nice thing about finite sets, that you can easily say when they're equal in finite time. And so yeah, and orbit finite sets are nice because you can represent them in a finite manner. You just say like what atoms are fixed, and then you say like what can we change, and then you say a particular element in the orbit, and with that element you can generate the whole orbit. And actually there is also like a language, so which I haven't described, called set builder language. And you can, so the theorem, there is a theorem saying that you can describe every hereditary orbit finite sets using this set builder language. And because the set builder is sort of like a symbolic thing, you can actually have algorithms, kind of symbolic algorithms working with that. And there's actually like a programming language using this particular expression. I think it's called looping over infinite sets.
Okay. Thanks a lot.
Thank you.
Any other questions? So, what can you say about atoms and well-foundedness in classical set theory?
I mean, so well-foundedness is kind of like we have it because we are using this von Neumann universe, right?
Mm-hmm.
So, okay, maybe I didn't understand the question well.
So, I mean, when you are taking anything like atoms, do they really play the role that you should not look inside them?
Yeah, exactly.
Yeah. Okay.
Yeah.
So like your search ends there.
Yeah, your search ends there.
Okay.
You can compare atoms. You can do things with atoms, but atoms themselves are not sets.
Are not sets, right?
Yeah.
You are just starting off with some set of atoms about which you cannot question, and then you build.
Yeah.
That, right?
I mean, so you can question, you can ask like, is this atom equal to another atom, or is it less than another atom? These kinds of things. But
like external questions, not internal.
Not internal questions. Yes, exactly. Not internal questions.
Thanks. If there are no other questions, let us thank the speaker. And I'm hoping that next week we will have one more student session. So Sujata, you might want to say something more, like, is this
Yeah, there will be. So Shreyas will be presenting next session.
Okay. So we
I
haven't
think
received any email so far.
But he submitted the Google form.
Yeah. Okay. Right.
Yeah. So
Right.
he already submitted the Google form mentioning the title and the abstract.
Right. Okay. I will.
It's there. But he is from ISI Kolkata, right?
No. He's from IISc, Bangalore.
I should change it because I didn't know it.
No, that's why I asked her to put his. I asked him to put his like official email address. If you see, it says iisc.ac.in.
So IISc Bangalore, right?
Yeah, he's from IISc Bangalore.
I need to change it because I just changed the logic.
He's a PhD student.
Yeah, he's a PhD student.
Okay.
But not a logic PhD student.
Okay.
Doing his PhD in crypto.
Right.
But he's interested in logic.
Right.
It's kind of a pastime for him. So
for this audience, I would like to announce that we'll have lectures on forcing after Navratri by Professor S.M. Srivastava. 2 lectures, I feel.
he kind of plans to complete everything within 2 lectures.
He said 2 1.5 hour lectures. So
That will be forcing literally.
Yes, I completely agree. But let's try to force him to do some more of forcing. Anyway, we will try. So me and Pujita will be meeting him. So we will try to force him to give more on forcing.
Okay. Fine.
Yeah, Arko, that was a very nice talk. So I
Thank you.
wanted to ask you something, and maybe it's a very vague question. So can you talk about continuum hypothesis or something like that? Because axiom not working there.
So actually the set theory is not as like ZFA. So it's not even a ZF because you don't have like other axioms. So it's kind of more, I think it's like a one Newman, but also maybe like a Grothendieck universe. You have union, intersection, like everything you can do inside this one. But because you don't want to insert too much of first order logic in the description. But actually, if you see this set builder expressions, which you can use to describe orbit finite sets, they use first order things. But yeah, so most of the things we have as axioms, which you can take, are actually the closure properties, which are these. Yeah, and actually, all the finitely supported things kind of says what things you can define.
Without choice, it's difficult to define cardinality.
There is actually not much sense of cardinality here, because even for orbit finite sets like X and X or and X cross X, sorry, not even for orbit infinite set X, X and X times X may not have the same cardinality.
Right.
But there are some things which work well. So I think Cantor's diagonal relation theorem works well. Okay. So the set has the same cardinality as the power set. This works well. Okay. Yeah.
So I'm pretty intrigued by these kind of sets. So this is something completely new to me. So can you please give us some reference?
Yeah. So maybe I can write in chat.
Yeah, please.
So there are 2 books. One is called slightly Infinite Sets by Nikolai Voyanchik. So this is he is a faculty in my department. And there is another book called Nominal
Voyanchik. Fine.
Sets by, I think, Andrew Pitts. So this Nikolai's book is more on automata theory.
Yeah, he is a computer scientist. So that is...
Yeah, but he also described like everything. So I might say something wrong in this talk. If you feel worried, you should go and check that book, and you will find the correct thing. Okay. And I haven't read the other book on nominal sets, but I mean, I have like seen a bit of it. I think that book is more mathematical because he defines them, but he also now then he goes to category theory sorts of things, like define what kind of category it builds. I think, but I'm not sure. Yeah, but this book at least slightly infinite sets, it's very approachable. It's like it's, I would say it's, you don't need to know anything to read that book.
Mhm.
Hopefully, some of the students would take up. Some of the students who are here. might-
Also, I should maybe mention my advisor here, because he also has like brilliant slides to for these things, like many slides for this topic.
Mhm.
Yeah, so those slides are also pretty nice introduction to this theory, and actually not even introduction, they also have some pretty nice theory inside them as well.
Okay. Yeah, thank you.